next we can put the heading as vector form of Coulomb's law. In this vector form of Coulomb's law, we can take the same figure, which is a positive charge, and let us take another positive charge. Okay, let us join these two. Okay, let's say this is Q1 and let's say this is Q2. Okay, so Q1 and Q2 are separated by a distance R. Okay, let's say separated by distance R. And suppose if this charge is exerting force on this, if this charge is exerting force on this and this charge is exerting force on this, how we are going to denote that force? Okay, so that we are going to write it first. That means this charge will be having some electric field around it, and this charge will be having some electric field around it. So this electric field will exert force on this electric field, and this electric field will exert force on this electric field. That is, the force exerted by Q1 on Q2 is, let us say, denoted by F12 vector. Is, let us say, denoted by F12 vector. That is, this charge is exerting force on this. So simply what we have to understand here is, when this is exerting force on this, that means this is pushing this charge Q1 so that it will be moving some distance in the same line joining. That is what we have to understand here. This charge is, let's say, moving in this direction because this is exerting force on this charge Q2. Okay, that is what is the meaning of F12. That means F12 is exerting on this charge Q2. That means this F12 is in this direction. F12 is in the direction in which Q2 is moving. That is what is the direction of F12. Similarly, if suppose Q2 is exerting force on Q1, then Q1 will be moving in this line joining. So that means F21 will be in this direction. That is, the direction in which Q1 is moving is nothing but the direction of the F21. So that is, the force exerted by Q2 on Q1 is equal to F21. Okay, these two will be definitely equal in magnitude but opposite in its direction. Let us show how it is, okay, how we are going to get that. So what is F12 vector is equal to? From this, F12 vector will be equivalent to, it is 1 by 4 pi epsilon. If it is not in free space, we should write it as epsilon into Q1, Q2 by R square. It's only the magnitude. This entire thing is only the magnitude. But what is its direction? This direction is always expressed in terms of unit vectors. So in this direction, it will be definitely having some unit vector. Let us denote that unit vector by A12. Let us denote that unit vector by A12, which is in the direction of F12. And when this Q2 is exerting force on Q1, there will be another unit vector which will be in the direction of F21, which we call it as A21 vector. That means this F12 direction is obtained by A12 direction. There A12 is the unit vector in the direction of F12 or in the direction of that Q1 which is moving. So next we can also write this F21 as F21 vector will be equal to 1 by 4 pi epsilon into Q1 Q2 by R square. Both are same in magnitude, but this is expressed as A21 vector. A21 will be the unit vector in the direction of F21. That is, in this direction F21 is there. So in the same direction we have the unit vector A21. So how we define this A12 and A21? So this A12 will always be equal to its unit vector is always defined as a vector by its magnitude. So it is going to give us the direction of F12, but we cannot take it here F12 vector by magnitude of F12. So this is always expressed as the position vector by its magnitude. So the position vector related to this A12 and A21 will be, we can use it as the position vector as R12 position vector, and here R21 position vector. So here A21 will be equal to, or A12 will be equal to R12 vector by magnitude of R12 vector. And similarly, A21 vector will be equal to, it is the position vector R21 vector by its magnitude, okay, R21. Okay, this is the way we should express the unit vectors A12 and A21 and substitute these two there. But how do we find out R21 here? R21 is position vector, but we also call it here because it is the vector between 1 and 2. Okay, so this is first charge and this is second charge. Okay, so whenever these two charges are given like this, R12 always represents, suppose if this is at x1, y1 and z1, and this is at x2, y2 and z2, if you want to find out R12 vector, it is always represented as R2 vector minus R1 vector. It is always represented as R2 minus R1. That means whenever you want R12 vector, this point minus this point, that is R2 minus R1 vector, is going to give us this R12 vector. So this is equivalent to R2 means it is x2, y2, z2 minus, okay, it is R1 which is x1, y1, z1. That means you get the vector as x2 minus x1, the x coordinates subtraction multiplied by ax plus y2 minus y1 into ay bar, y2 minus y1 into ay bar plus z2 minus z1 into az bar. This is how we are going to calculate R12 vector. But if we want magnitude of this R12, then we can get this as, okay, under root of this expression, that is x2 minus x1 whole square plus this is y2 minus y1 whole square plus z2 minus z1 whole square. This is how we are going to get the magnitude. So this R12 by magnitude of R12 is going to give us this A12. But what about this A21? A21 is obtained by R21 vector by magnitude of R21. So this is R1 vector minus R2 vector. R1 minus R2 means what? R1 is x1, y1, z1 and R2 is x2, y2, z2. So this is going to become x1 minus x2 ax bar plus y1 minus y2 ay bar plus z1 minus z2 az bar, and magnitude will be same. So this R12 vector x2 minus x1 ax bar and A21, that is R21 vector, it is x1 minus x2 ax bar. So this R12 vector and R21 vector both are exactly opposite vectors because R12 is in this direction and R21 is in this direction. So we can write this as R12 vector is always equal to minus of R21, but they are equal in magnitude. If you take magnitude, they are going to become equal, but if you take direction, they are exactly opposite. So based on this condition, we can also say that A12 will be equal to minus A21 because this A12 is equal to R12 by magnitude of R12 and A21 is R21 by magnitude of R21. So they are also exactly opposite. So because A12 and A21 are exactly opposite, because they are going to give us the directions of this F12 and F21. So we can write here finally as this F12 vector will be equal to minus F21 vector. So this is the final conclusion of the Coulomb's law in vector form. That means these force exerted by Q1 on Q2, which is F12, and force exerted by Q2 on Q1 is F21. They are exactly equal in magnitude, but they are exactly opposite in its direction. Okay, this is what the Coulomb's law, okay, in vector form is going to give us. Okay, so we can see problems, okay, later. Okay, once we complete the entire analysis, okay, we are going to see the problems on it. Okay, so next, after this Coulomb's law and Coulomb's law in vector form, we have the force exerted by some system of charges on a single charge, which has actually given the definition of electrostatics. Okay, so that part we are going to see here, because most of your problems will be based on the force exerted by some n number of charges on a single charge. Okay, how we are going to find out that? Okay, let us try to see that first. So the heading will be the force exerted by system of charges or n number of charges, system of charges on a single charge. Force exerted by system of charges on a single charge. Okay, how is that? Okay, we are going to see how we are going to find the force on a single charge due to a number of charges. Okay, let us see the figure first. Okay, so for that, let us see there are some n number of charges. Let us say like this. These are all the point charges. Okay, these are the n number of charges. Let's say this is Q1. Let's say this is Q2, Q3, Q4, so on. The last charge is Qn. Okay, and there is another charge which we are taking here. Let's say this is Q0. Let's say this is Q0. Okay, now to find out the force exerted by this Q1 on Q0, and Q2 on Q0, and Q3 on Q0, Q4 on Q0, and up to Qn on Q0. So to find out that, as we have already seen in Coulomb's law, to find out the force of attraction or repulsion, we always need the third statement, as always the force acts along the line joining the 2 point charges. So we need to join the 2 point charges between which we are finding the force between them. Okay, this is line joining Q1 and Q0. Okay, next line joining of Q2 and Q0. Next line joining of Q3 and Q0. Next line joining of Q4 and Q0. And line joining of Qn and Q0. Okay, so we have joined all the line charges. So now we are going to find out the force exerted by Q1 on Q0. That means that arrow will be always towards Q0, because this is applying force on this. We are not worrying about whether Q0 is exerting force on Q1, Q2, Q3. That we don't require. So that is neglected. So here all these charges are exerting force on Q0. But how can we measure when all these forces are exerting force on Q0? Is it possible for us to find out at a time? It's not possible if you try to find out the force exerted by Q0, okay, by all these charges at a time. So what we have to do is, we have to find out the force exerted by Q0, okay, by a single charge Q1, that is separately, plus, okay, the force exerted by Q2 on Q0 separately, the force exerted by Q3 on Q0 separately, the force exerted by Q4 on Q0 like that, the force exerted by Qn on N0. This is what we have to do it, okay, while finding out the n number of charges. That means we have to apply here superposition principle. So superposition principle always says that, or states that, you have to find out the force on a single charge by individual charges. That means when you are finding out the force, okay, on Q0 due to Q1, think that these charges are not there. These charges are not present. Remaining charges are not present. Only Q1 and Q0 is there. Q1 is exerting force on Q0, and we can easily measure the force between 2 point charges. Okay, so next, when you are measuring the force exerted by Q2 on Q0, think that Q1, Q3, Q4 are not present, only Q2 and Q0 is there, and you can able to measure the force exerted by Q2 on Q0. Similarly, we can find out all other charges. That means to find out the force on Q0 by using system of charges, we have to apply superposition principle. So we can write this as from superposition principle. From superposition principle, okay, we can write this as the total force on Q0 is equal to the force exerted by individual charges. But how can we denote those? Previously, when force exerted by Q1 on Q2 is denoted by F12, that means first charge exerting force on second charge, that is represented as F12. But here that first charge is Q1 and the second charge is Q0. So this will be indicated by this force, we should call it as F10. And what is a unit vector in that direction? We should call it as A10. And what is a position vector there? That is called as R10. Okay, similarly, here the force exerted by Q2 on Q0 will be F20. And the unit vector in that direction will be A20. And the position vector will be R30. Similarly, that force will be due to Q3 on Q0 will be F30, and the unit vector in that direction will be A30, and the position vector will be R30. Similarly, the fourth one A40 and R40, and the force will be F40, and similarly the last one will be Fn0 vector, and the unit vector will be An0, and the position vector will be Rn0. This is how we are going to write all this. Maybe confusing here, but okay, you have to write all these unit vectors, distance vectors and forces to get the total force on this Q0 will be equal to F10 plus F20 plus F30 plus F40 plus so on Fn0 vector. Okay, this F10 vector can be written as, this is equal to 1 by 4 pi epsilon. If it is free space, we can write it as epsilon naught, but it is in a medium. Okay, so we can take it as epsilon only. So Q1, here F1 means Q1 and F2 means it is Q0 by R square. Okay, so into the unit vector which is related to that is A10. So we can write it as A10 plus 1 by 4 pi epsilon into Q2 Q0 by R square into A20 plus so on. The last force will be Fn0. It is 1 by 4 pi epsilon into Qn and Q0 by R square. The unit vector related to that is An0. Okay, so from this we can simplify this further as what is common in all this is 1 by 4 pi epsilon into Q0. Okay, the distance may be different here. Okay, because it is R10 and this is R20 and this is Rn0. The distance may be different because this and this distance may not be similar. So let us call this as R10 and this is R20, R30 like that. Okay, so this can be written as 1 by 4 pi epsilon into Q0 is also constant. You also bring out Q0 by, okay, that is Q1 into R10 whole square into A10 plus Q2 by R20 whole square into A20 plus so on Qn by Rn0 whole square An0. Okay, this can be further simplified it as Q0 by 4 pi epsilon into sigma I equal to 1 to n. This is Qi by, this is Ri0 whole square into AI0 vector. So this is the total force on a single charge Q naught, okay, due to system of charges can be expressed like this, and we can able to solve many problems by using this particular expression. Most of your problems will be given like this, by giving 3-4 charges which are placed at the corners of a square or corners of a triangle or corners of a rectangle, and you are asked to calculate by placing a charge at the center or somewhere, and you are asked to calculate the force exerted by all these 4 charges on a single charge under equilibrium conditions and other conditions. Okay, like this we can able to solve the problems by using this Coulomb's force law. Okay, so next we are going to find the electric field intensity. Okay, let us see the definition of electric field intensity and its expression.